Hello everyone and welcome to a new video tutorial. Today I'm going to teach you how to do some solar analysis and radiation analysis using Ladybug and Grasshopper. So what is Ladybug? Ladybug is a set of tools for environmental analysis. These tools are available in the website. You will be able to read them and understand them, but the different tools and plugins. One is Ladybug, the other is Honeybee, Butterfly, and Dragonfly. Each of them has different type of functions. The Ladybug will focus on renewable energy, indoor and outdoor thermal comfort, while Dragonfly will be, for example, for urban heat island simulation using the urban weather generator. Honeybee will focus on radiance and indoor quality. So it uses Energy Plus or OpenStudio and Energy Plus, while Butterfly will focus a little bit on HVACs and airflow analysis. So for today, we're just focused on Ladybug and very simple tools. You have to go to Food for Rhino and download all the tools. Recommend the latest version available there, July 13, 2020, which is the Ladybug 0.069, the Honeybee Legacy with legacy plugins. So when you have installed that, you will have this set of plugins in your Grasshopper uh, canvas. Now, the first step is we need to bring the Ladybug component into the canvas just to be sure we're working correctly with the right version. Now, what we have done this, we should be able now to bring the EPW file, which is an EPW. An EPW is it's a file that contains all the climatic information, the meteorological information for a particular site. So in this case, there is a website, ladybug.tools/EPW map. So you can find here all the different weather stations. Some of them are discontinued, so you will not get a data with information. Many others are very useful and it has the information. So our case study is in Adelaide. I chose already Adelaide, Kent Town, and you just put download, click there, and automatically will be downloaded at the bottom. When it is downloaded, we go to our folder, and then we just have to extract all the information here, and you will have here the EPW. If you open this, we'll try to open it with Notepad, so you will understand that EPW is historical data of a typical meteorological year. So this represents how it is a typical the typical climatic conditions for that particular location, and you will have a lot of information here, like solar radiation, maximum temperature, minimum temperature, and other information regarding to rainfall and wind speed, etc. So once we have that, there are two ways we can collect that information. So if you go here, we can import EPW file, or you can also put download a DPW file, but download EP weather file, and the output will be the input here, and so you can download it, or you can do what I've done before. So here we're gonna put a file path, correct, and we are gonna set one existing file. We go to our tutorial, and then we find the EPW. Should be here. Let me just open this properly. It should be here. Yeah. EPW. So you know that this is the EPW file. That's it. This is the one that we choose. So we put open. It will take a couple of seconds, and it's calculated the location. So once we have that information, now the next step is for the solar analysis, we need to calculate our sun path. Okay, So for the sun path that it is in environmental analysis, you go for Ladybug sunlight hours analysis. Oh, sorry. You need to identify the find the sun path. So it should be here in the weather data. Ladybug sun path is here. Okay. So we need to connect the information here. So one of the informations that is critical is the north. By default, there are some values here. So it's assuming the y-axis of the Rhino model as the 0 degrees. So if you go here to the top, assumes the y angle as a north. But if you have another north, you need to define a new north. And you can do this creating a vector 2-point. So you say vector 2 points. Okay, and you need to define the point A and the point B. So one it is the point, point, and you create another one. So one will be the point A and point B. It's really important you define which is the point A and point B will define the direction of the vector. So that is very important when you display the vector. So you can create here a vector display. Okay, so to display the vector, here's the vector, and the anchor point should be this point, and this should be the point B, which is where you anchor, and the direction will be defined point A. So we define 2 points, so you can say just put set 1 point, and the point A should be here. Sorry, we need to put set 1 point, type point, sorry. We can draw the points here. Let's turn on the snaps. Yep, so we define here 1 point, then we draw the other point here. So we can define the points, set 1 point, and then we set the other point. So you see what is the direction of the vector. Okay, once you have the direction of the vector, you know what it is the north pointing, so you know that it is correct, and you get this vector and you just connect it to the north here. Okay, well, we'll move this one here, and let's save this one. So I saved that. So once we have the north defined, we need to get our location. So where do you get the location from? The location comes from, of course, the information of the EPW. So if you connect here a panel to different of these outputs, so you will be able to read here all the information that you need: longitudes, latitudes, time zones, etc. More information about the latitude, the output, etc. So let's keep the panel somewhere there. So let's disconnect this. Okay, let's disconnect here the panel. Okay, so we get the location from here, and we just connect it here. So we have the location. Let's go back to analysis. So you start seeing here the, let's delete this one here. So you still start seeing here the sun path. Okay, and once you have done this with the sun path, then you can define the hour and the day and the month and all those information. So we don't need to display this anymore. And we're coming here is define the hours. So I want to know what happened is the hours should be between 0 and 24 hours. In fact, it's not like that. It should be between 1 and 24. Okay, so we put hours. So this is at 1 a.m. Of course, we can define it at 11 a.m. So this is at 11 a.m. We need to define the day. So the day should be between 1 and 31 of the month. Okay, the day, first, or we can put the 10th, and the month should be between 1 and 12. Sorry. Okay. So the month should be, this is January then. So this is how it is in January, the same day in January, February, March, etc. And this is in June, so it's winter, right? So different periods. So now what you can do is define the center of this. If you want to show it or display it in the middle of them, you can define the center using a point. And again, you want to use a point, maybe this is the center part of your model. So you set one point, grab it there, and then you just grab it to the center point. So now you visualize this in your model. Okay, so that's the north, correct? And this is your model. Now, once you have done this, you can also define a scale. So let's imagine 1.5 times so it will grow your sun path, so you will be able to see better, or you can make it much larger. I think this is too large. Let's define something between 1.0 and 2.0. Okay, so this is a good side. This is the scale. So it will increase a little bit the scale. Okay, so when we have done that, we can also scale the size of the sun. So we can say it's the same scale, so it will be 1.3 times, or you just can create another one that is two times the size. So you will see the sun there shining. You can add projections, so other information, but that is not the central point of this tutorial. But anyway, you can add other information. If you want to know what are all these different, so you can all these different parameters and inputs and outputs. So you just can click on top of it. So projection is a number of set projections to the sky hemisphere. The default projection, the default is set to draw a 3D hemisphere. Yeah. So that is what we want. Or if you want an orthographic or you want a stereographic, which are these projections that you see here in red color. Okay, so you can change the type of projection. We'll leave it as default. Now on the other side, the output, you will have different information, which is like the sun vectors. So it is indicate the direction of the sunlight, and then so you can visualize it that if you want. So we can use, what you need here is I think is a curve. Let's see if it works like that. No, so because it's a vector, it will need a vector information or 2-point vector to visualize that. Okay, so we're going to use this information of the sun vectors, which is basically the direction of the sunlight, as an input in our solar sunlight hours analysis. So for the analysis, what we need to do is bring this one, the Ladybug sunlight hours analysis. Okay, so what we're going to do here is just basically bring we'll bring it down here so we have enough space. Let me save this. We're going to bring these sun vectors, okay? And we are going to then run the the calculation. So the sun vectors here goes into the sun vectors in this component. We can change the north, but in this case we use the default because we already calculated before. And we're going to use other information that is critical, like which is the geometry and the context. We can also define a grid size, and a grid base. So the first thing is the geometry. Geometry is which is the sunlight analysis will be conducted. So it's our B-reps, meshes. In this case, it can be the surface plus the buildings. So I prefer to use as a geometry the surface at this point, and then later we will see and where will be calculated. So we just put here surface, or you can use a B-rep. Okay, B-rep, and you set this one B-rep to the okay, and we just connect it to the geometry, or we can use also surface. Okay, and set up one surface, and we set up the surface, and we just connect it here to the geometry. Okay, we don't need to visualize this, so we can turn it off. So once we have the surface, we also need buildings. Okay, so the buildings are a collection of B-reps, which is will define our context for the analysis. So if you can turn off here the layer, okay. So if you have here B-reps, so you just click put B-reps, or sorry, B-rep, and you can define multiple ones. Define multiple B-reps, and just select them like that, and put enter. And then you can change here the name to buildings. Okay. So once we have done this, we just connect these two contexts. Okay, so we have our context. We don't need to display this anymore. So now it's time to define our grid size. I will use just one. Or it's good to, sorry, 1, 2, 1, 2, 3. Okay, so you can change the size. For now, it's just one is the grid size. And then we need to define our distance from the base for the calculation. So you turn on this again. The distance from the base, we can say 0.1, 10 centimeters. Okay, or 0.1, 0.5. Then we just reduce this to 0.1. Okay, so this is the distance from the base, so it will be elevated a little bit so we can be able to visualize it. Okay, and after that we need to define a toggle bar or boolean toggle to turn on and off or run it or not our simulation. So once we have done that, we click on, and it takes a little bit until the simulation is run. So you can see here, say 0 hours. There's obviously something wrong. So I wanted to do this because they definitely they calculated wrongly. So we turn it off. So the two things we have to correct here. Okay, turn off this simulation. There are two things we have to correct. The first thing is that the buildings should be inputted in not only the geometry, not only the context, which is where is for the calculation, but also the geometry for the calculation. So we just drag and you just click shift, and at the same time you connect it to the geometry. And another problem is that the surface sometimes is upside down, so we need to flip the surface with flip. Sometimes happens, sometimes not, so we just need to do this, disconnect here the surface, and then reconnect the surface. Oh, sorry, reconnect, adding shift. So now we have as a geometry the surface, okay, and the buildings. And the context for the calculation of the hour is, what that means context is what objects are gonna generate a shadow or shading, okay? So it should be the buildings. And now we go there and we calculate the simulation. It will take a bit. So now it is here. So you have the number of hours of sun that will receive them within the period of analysis. So this is just one particular hour, right? Because our um, here our information is just for that particular hour, 11 a.m. This is the sun at on 10th of June. If we move this one to, well, I think mess up the things earlier in the morning, you will see that this should change. So now it is at 7 a.m. so it changed. Now, what we want is just to not calculate the number of hours. We know that this will be 1 hour, 0 hours, and the other one will be 1 hour. This is meaningless. What we need to know is calculate the amount of solar radiation during the whole day, for example, on a summer day. So what we're going to do is we are going to turn off this, and we're going to pick our analysis period. Okay, so we're going to a day, summer day, which is 11 of November, or 20, yeah, 19 of January. Wait a minute, that's January, and we want it for the whole day. So what we're going to do is we are going to change here our analysis period. We are not going to rely on the hourly analysis. So our analysis period should run for a particular number of hours or time period. So we'll show you how to do that. So for the analysis period, we go here to analysis weather data, and then you put analysis period. Okay, so we input that here in the analysis period. Okay, it will take a bit because this will also be running all the time, and it will change the information. So one good way to avoid this extra time for calculation is just to stop all other simulations or turn off the visualization, so it's much easier. Okay, so that's what we're going to do. We don't need the visualization of this sun path, because otherwise we'll make our model very slow. So as you can see, these are all the suns that were calculated, so we don't need that information, so we turn it off. Okay, that it will be much faster. So our analysis period will override this information of hour, month, and day. So we need to define again from which month to which month, from which day to which day. So basically here we start again with months. So we can grab here month, this is the month, and run it here and copy. We want it from January. Okay, that's another problem, is it's calculating again and again. So what I'm going to do is I'm going to disconnect here and just connect it once. Okay, so I just want to wait a little bit. So what I'm going to do is I'm going to disconnect this. Disconnect. Okay, so now we're going to run it from January till, I want a daily. So if it is a daily calculation, you just need, it has to be the same month. It has to be the same date. Okay, so you can have it like this if you want, or you want to have it like this, same day again, or just copy and put to this day. And then we need to make some space for the hour. So let me grab this one here. And the hour, it comes from here as well. So I want a day from 7 a.m. till 7 p.m. 7 p.m. Okay. So once we have done this, we save. Now we connect it. That way we avoid again and again the sunpath to be updated, and it takes a while. So now we go to analysis period. We copy there. And once there, okay, that's good. We can disconnect the rest or just leave it like that. Should be fine. Okay. Now, once we have done that, Now we're gonna do again our analysis here, and we turn it on. And that's it. So you can have here now the number of hours for several, um, um, sorry, for the whole day, for several hours. So we turn off this because this is much easier to visualize, okay? So now you can see here the results of the solar analysis. So this sunlight hours, so it's the number of hours. So you can calculate which areas will be overexposed or underexposed, but this doesn't give you that much, information in terms of the color, perhaps. But there are other ways to visualize this. So you have to change your legend. So if you go to the extras and you go to Ladybug legend parameters, then we will be able to change the legend. So before connecting, we can change the lower bound, the high bound, the number of segments that you want in between every half an hour, for example, or custom colors. So as you can see, the custom colors, you will need a gradient library. Okay, so for custom colors, you need a gradient, Ladybug gradient library, and connect to the custom colors. So you will have here different indices, different type of colors. So 0 is for the original Ladybug, and for example, you have thermal comfort colors like UTCI. You have black to white. Perhaps the black to white works pretty well, which is the black to white is the number 16. So you just put here, we have here number 0 to 23. So we just put 0 to 23, and we choose the number 16, which is the one that we want, black to white. Okay, and we can change other information here. We can add a legend scale, reduce this legend, for example, to 0.75, the size that it has, because it's too big. We can change the location, etc., and change the font if you want a specific font. So we go with this to the legend parameter. It should change the legend, but it will take a bit because it has to rerun the simulation or the calculations. So now you come here and you see we have a problem here with the surface. I think it's this one. Let's turn it off. So now you have here a completely different set of colors. We can go to top. So this shows how many hours will be exposed to the sun. So we have more than 12 hours, all the roofs, obviously. In the middle of this, between 5 to 10 hours, because it's obviously there's no shade from buildings. But here in between buildings, you will have less than 2 or 3 hours. So you know which areas will be overexposed and underexposed, or overshadow it and undershadow it. And you can generate this for different times of periods of analysis. So I'm not going to touch the period of analysis. So you can bake this information by right click and baking it, for example, the context match or the results of sunlight hours. So you have a lot of outputs here after the estimation. And that is not what we want to do now. It's just simply to visualize the sunlight or solar analysis, sunlight hours analysis. Okay. This is one thing. Now, the other thing I want to do today is radiation analysis. So the radiation analysis is different because it will calculate the amount of kilowatt hours of, energy that the surface will receive during the whole day. So if you go here to environmental analysis, you go to radiation analysis, and if you want to read what it is, so this component allows you to calculate the radiation falling on this geometry using a sky matrix from the select sky matrix component. Okay, it's useful for building surfaces such as windows, well, anyway, will help you to understand the solar heat gain. Okay, and this is critical for outdoor spaces, for outdoor thermal comfort. For example, for vegetation growth, there are different applications you can use from this, and it's also you can generate this as an input for other components or other calculations. So we have here the radiation analysis. So before the solar radiation analysis, we need to have another component called select the sky matrix. So you just right click and you put select sky matrix. You can see we don't need to show this anymore, and we can turn off the toggle. Okay, so far so good. Okay, so for the radiation analysis, we put the select sky matrix. We need to define again the node, the geometry, the context, the grid size. We can try defining different grid sizes. Depending on the grid size, it will take longer to calculate. So I will leave it like that with the default. And the distance from the base, I will just copy from the one here. Distance from the base. You just have to click Alt, and then drag it, and then you will have a copy of that component. So this is distance from the base. And now we have the orientation study parameter, which is something different. Now we need to connect here later the sky matrix. So for the sky matrix, we need the cumulative sky matrix, which is another component. And we need the component called HOI, H-O-I, which is our, that stands for selected sky matrix, the hour of the year of the analysis period. Okay, we want to do it, and then we need to define our analysis period. We need to remove diffuse or remove direct sunlight, or remove diffuse component of the selected sky. So we are going to left some things default, and what we need here is in fact two basic components. Okay, so the first one is the generative, the cumulative. Sorry. You just put cumulative, and is this one, the Ladybug generative cumulative sky matrix. And for that, we're going to need the EPW file. So we just go again to the EPW file of the beginning, right? And then we write it there, we grab it there, and we just connect it there. Now, we can leave the rest as a default, but we can modify this, which is the sky density, or the number of sky patches, okay, for generating the radiation. The working direction, and all these things we can. This is the working directory, so where all the simulation outputs will be put, and then we need our boolean toggle. So we need to do the boolean toggle. So this boolean toggle goes there. So that's the first thing we need to generate. So we just put true, and it will start generating the information that we need. Okay, so you don't close anything, you just leave it there. It's calculating the diffuse component. When the calculation is done, all that information will be stored here. That's why there is a working directory, okay? So it finished. I think it finished. It's still thinking. Still thinking. Just give it a couple of seconds. Okay, that's it. Now we grab the cumulative sky matrix and we just connect it to this component. After that, what we need is to define the analysis period. Okay, so for the analysis period, we can copy the whole thing from here, or we just can connect the same analysis period, or we just can grab it, drag, click out, and then drag it down there. Correct. And then we just connect analysis period. The analysis period can be for the whole day, or can be between different months, a whole complete month. So for example, from January to February. Okay, so we just put here analysis period, and also change the number of hours, so from 6 a.m. etc. So I try to keep this as simple as possible, run it early anyway, daily, makes sense, or for the whole month if you want to calculate for whole summer. Okay, so we just connect there. So not trying to mess up with these things too much. Is for the same month, for the same day, and from 7 a.m. to 7 p.m. I want to know in one whole summer day how much radiation it's in each part of the surface. So once we have that, we need to connect our selected sky matrix to here. Okay, and now we need to connect again the geometry. Okay, and we need to connect again our context. So like previously, this surface should be my geometry. So I put shift and also my buildings. So I click shift and connect both. And now the context should be only the buildings. And I added just directly there. Grid size, I will use the default for now, and then we will see what is the result. Okay. And then I think we need to also use a Boolean toggle again. And I recommend you to put in parallel and connect it to run it because this will use parallel computing, okay, to increase computational power. I save it. I always recommend to save it for running anything, and then let's run it to see what is the sort of output that we get. Okay, so just run it and let's see. So that's it. That's what we got. Again, we turn off our context. So you have here a completely different map or graph. Why? Because here we calculated a kilowatt hour it's the amount of energy that per square meter that will be that each pixel will receive or each grid will receive for a whole day. So you see that obviously the roofs are overexposed with more than 4.51 kilowatts per hour. So they have a um, higher radiation. This will determine also what type of material. So if you have here heat absorbent materials, for example, with a very low albedo like asphalt or concrete, so you will see that all the central area of this, let's say, plaza will absorb a lot of heat. So you can plant grass if you want, for example, here. So it helps you to inform in an intuitive way what you want to achieve in terms of performance. And also, if you want to install PV panels, in which surfaces you will get higher, let's say, solar exposure or more kilowatts per hour, you will have a higher production, of course, of energy. Makes sense? So this, if we look at it, this all of these are south facing or southeast, southwest facing of facades. So we will receive minimal amount of solar radiation. Here we're going to the east, and then it will move towards the north. This will be overshadowed by this building. So, and here you see the buildings generate kind of effect on it, creating shading, and obviously the areas in the middle of the central area of this um, street or plaza will be overexposed. So this is what it shows the radiation analysis. Again, if you want to use a different legend, you just have to drag and click Alt and change the legend. So here, I think which legend we have. Wait a minute. We can use different colors. Let's use the thermal comfort UTCI, cold hot hours, um, radiation benefit, sunlight hours, ecotech. We can use, this is the default, but maybe we can use the number one, no, the zero. Let me see, is zero? No, it's zero. Or, no, yes, we can use the default one. And we go to the legend par. So we'll see. It will generate up again. Oh, so you can play with the visualizations, changing the sizes of the legends, changes the orientation of the legends. You can see the legend here is oriented in a different angle. Um, but it's good because it tells you here. Um, okay, it tells you the. I think machine needs a little help. Yeah, it will tell you the. I think this is the default one. Anyway, so it will tell you here from which day to which day or which period of analysis has been conducted. So very useful information for your climate analysis. I also would like to add a couple of extra components here that maybe are going to be useful for you, um, which is the Windrows. So you can click Windrows. Um, you have the radiation rows, but then Ladybug Windrows. Where is the Windrows? I will find it. So here it is. You go here to visualize weather data, and then you put the Windrows. So we can move it maybe somewhere down here, perhaps. Yeah. So for the Windrows, again, this is much simpler because it's not. There is no need to run the simulation. But I want to do something. So we have here Windrows. We will need the hourly wind direction, and we can get this information from our import EPW. So we have here the hourly wind speed. We need the wind speed. So we put here hourly the wind speed. I will turn it off for now. Then we need our wind direction. Okay. So wind speed and wind direction. And then we need analysis period again. Um, we can define a new analysis period or just copy it from here. And we put analysis period here. I will change this later. We need the center point, so we can use a point and set one point, and we set this point in the middle. I like when the windrows like some way overrides or overlaps the geometry or the side, so it can help me to understand where is the wind blowing, which places will be uncomfortable in winter or in summer. So let's grab this point and put it in the center point, right? We don't need to show this point. And then the analysis period, for example, particularly in summer or in winter, I want it from on 5th, oh no, in June, the day the 25th, okay, so solstice, no, 26, or in the middle of the winter, 7 July, July 20 or 21, from 7 a.m. again to 7 p.m. till 7 July again on the 22nd. So it's for from 7 a.m. to 7 p.m. Okay, so that's our analysis period. And I think we don't need any, oh, we can add more information if you need. But at this point, and then we just can need, we can put a toggle, Boolean toggle, sorry. Boolean toggle. And that goes into, gosh, run it. So we can run it right away. So, well, we can now visualize it. So you can see here, well, we needed just to turn off the radiation. Okay, so you can see here now the windrows overlapping. We can make a displacement from the base, so we can move it. But I think we can also change here to wireframe. So this wireframe is very useful, okay? So we see where is the predominant wind direction from in summer. So, oh no, sorry, in winter. So we will have a lot of wind blowing um, from east and also from northwest. Now, what we can do is modify a little bit. So I want to know in the morning. So up to midday, the wind will blow usually from, it will be northwesterly wind, predominantly, and the speed will be around 7.7 meters per second. Okay, so it will come from this direction in the morning. So this could be particularly unpleasant if you want to create a windbreak here, etc. But in the afternoon, what I want is to calculate here. Um, sorry, I want to set the value to let's think about it. Maybe in the afternoon from 4 p.m. or 1 p.m., 2 p.m. till 7 p.m., 8 p.m. So you will see in the afternoon the wind will blow from a different direction. So all this street will be well ventilated, while all these areas in this part of this plaza or square will be less ventilated. Of course, we need a more precise and accurate analysis, but these at least give us an idea of what to do, and which type of wind speeds and direction of the wind to consider. But we're definitely for our thermal comfort, we need more to analyze more aspects. This will be too simple to think that this information is enough for our thermal comfort. We need to consider other factors. Okay, so I will disable this. Oh my gosh, it doesn't let me to disable the preview, and I will just stick to this preview because it's a very interesting one, and hopefully it doesn't have to run again unless you run it. And when you use the wireframe here, look, it's shaded, but when you use the wireframe, you can have a very interesting visualization with all the outlines of the buildings. And you can then save this as a photograph, and you can change the background if you want to white, and then it's ready for analysis. So that's all for today. It was a bit long tutorial, but I hope this tutorial has been very useful for you to do some very basic environmental analysis, sunlight hours analysis, and ladybug radiation analysis. But I recommend you to explore other ones, and then in future I will come back with more exciting and interesting computational simulation for environmental purposes. So see you next time.